Right, machines and frames can be sometimes simple and sometimes incredibly complex. Here we have one that is somewhat simple, and we'll get complex ones here in just a little bit. Right? I say somewhat simple because, well, remember, the first thing we want to do is we want to identify what is it we're supposed to find, the external reactions. We also want to find out how many members we've got. Okay, well, we've got this bracket ABC, and then we have a separate straight member CDE. Only two members, but we also have this cable and this pulley here at D. That begins to make this a little bit more complex along the way. But we're just trying to find the external reactions for the frame, and that might seem like it's pretty easy. After all, we got a pin support, so gee, that would be EY and EX, and another pin support, and AX and AY. So that's easy, right? I mean, that should be easy. Oh, that was the global free body diagram business, right? So you really should do this down here. And note, there are some things we can get out of this global free body diagram that might turn out to be pretty important. But there are some things that we can't get out of it. So notice that we've got ultimately here, we have 1, 2, 3, 4 unknown reaction components. We have 3 global equations of equilibrium. That makes this initially not tractable. We got one more unknown than we have equations. So that might be called statically indeterminate, but it's going to be this pin at C that's going to be the key difference here, and you'll see that in just a second. Right, so it turns out that we have +1 special condition at C. Right, and that's going to give us 4 pieces of information that will be critical. So when I said in just a minute, I really meant literally in just a minute. When you go look at point C, there's no internal bending moment. We pull that pin, and all we're going to have are X and Y components. I don't know what direction they might be. We'll probably try to do some analysis to maybe begin to figure this out. We've got AX and AY over here. I've already started to show them in a specific direction, so I'm going to be consistent and not be changing this things up all over the place. It might make it very difficult if we're not consistent between all the free body diagrams. In fact, I'd say it's almost impossible if you aren't consistent. So let's go look and see what we can actually get here. If we sum moments about point A, notice, and let's take counterclockwise positive, we'll have minus 700 newtons times a moment arm that is now 4 meters plus a 7 meter moment arm times EY. EX, AX, and AY all go through point A, so they're not in there, and therefore EY is going to be equal to 700 divided by 7 is 100, so that's going to be 400 newtons for EY. Right? Likewise, we can sum moments about point E, and we'd find something similar here, that, okay, 7 times AY minus 700 times 3 meters would be equal to 0, therefore AY would be equal to 300 newtons. Right? And then we'd be kind of stuck here. Sum of forces in the X on that free body diagram, all we're going to get is AX minus EX equals 0, so therefore those two are equal and opposite, but that's all we know. Right? And that's that notion that if we don't use this special condition at C, we don't have enough information to uniquely solve for all of the reactions. We can solve for some, but not all. So let's see what happens. We come down here to C. We now know that come down to the free body diagram of ABC. We now know that AY is equal to 300 newtons. Right? Now, we've got this cable at B, right? And that's one long cable, and it's at 700 newtons, no friction in our model, so therefore the cable force is the same throughout as it wraps around that pulley, so that will be 700 newtons. right? And so look at this though. If we sum moments about point C, then I think we can go find AX, and then we'll have EX and we'll be done. So sum of moments about point C, let's take counterclockwise positive, so we'll have minus 300 newtons times 1 meter, and then plus 700 newtons times, also 1 meter, and then we've got to get plus 3 meters times AX, and that will be equal to 0, right? The CX and the CY values don't get involved in this. I still don't know their directions yet. And, ooh, this is kind of weird. 700 minus 3 is a plus 400, so 3AX is equal to a minus 400 Newton meters. And so AX is equal to a minus 400 Newton meters divided by 3 meters. Meters cancel out, so minus 400 over 3 newtons. The minus says I guessed wrong about the direction of AX. It is actually in the other direction. Well, that's kind of a little bizarre, right? So I did this in markers so I cannot erase and show the forces in the other direction. So I'm going to be stuck here with the opposite, right? Minus means opposite. In reality, EX actually is going to the right, 400 divided by 3 newtons, and AX is going to be going to the left at 400 over 3 newtons. Right, now that seems a little bit weird, that actually this thing wants to close up on us and we need the supports to keep it held open, and it's all happening because of this cable force that the 700 Newton effect has is a gift that just keeps on giving. It pulls down on the middle, but it also creates an interesting thing that happens there in the middle horizontally that we wouldn't have had if the if this hadn't wrapped around like it did. It's kind of an interesting little thing that's going on, right? It'd be real interesting to say what would happen if we just hung 700 newtons off a point D, didn't wrap a cable around it, this cable was completely gone. Then what would happen? That's another interesting one to take a look at. Right, so we ended up with something kind of interesting here. Got all the reactions. We had to do the global free body diagram. We did a member free body diagram. We were in, we were out, and we came up with a surprising result.